optical fiber UART with the wave division multiplex. Wait, what is this guy even talking about? You see, a few days ago I got my hands on this EMONA FOTEX optical fiber kit, and through this kit you can do experiments about optical fiber very easily. But why do I need an entire kit to do experimentation on optical fiber anyways? Experimenting on optical fiber is a little bit tricky. The first step for experimentation in optical fiber is that you need to convert light to electricity and electricity to light. This is important because all the chips that we usually use are based on electricity, right? The gates and the MOSFETs, everything inside them is run through electricity. And wait a second, is this guy saying you cannot do logical operations on light? Does this guy know about photonic ICs? We do have photonic ICs, but they are not like conventional yet. Yeah, which is another way of saying he doesn't have it. So we need a way to convert those electrical signals into light signals, and the light signals back into electrical signals. Then only we can do processing, right? So this EMONA FOTEX board works with NI Elvis 2, and you can use LabVIEW software to configure everything, but currently I will not use LabVIEW software. I will directly get a signal from the board itself. You can see all the sources, and I will plug it into the transmitter LED. So this terminal converts electrical signal into optical signal. I will take the optical fiber cable provided into the kit. This is the optical fiber cable, and I am going to plug it into the transmitter LED, and you can see the optical fiber carries the light. Okay, the light is being carried over here using the optical fiber, and I have put into the receiver side. You can get the electrical output. So here I am sending 100 kilohertz digital signal through the transmitter, and you can select green or red, and these two are the LEDs available on the board. Here I am transmitting using red, and on the receiver let's see what we get. Okay, so what I will do is I will connect my analog discovery oscilloscope. So this is the digital output connection. I have connected it to my analog discovery's oscilloscope port, and the ground is also referenced over here in the oscilloscope, and you can see on the waveform software we are receiving 100 kilohertz square wave over here, right? And we are basically getting it on the oscilloscope. And next off, you can see the level here is 5 volt. Okay, so this is outputting a 5 volt level. This is not safe for our FPGA, so we will create a voltage divider. Okay, so we need to create a voltage divider since our FPGA does not take 5 volt input. It basically runs on 3.3 volt input. It is a 3.3 volt system. So this is the voltage divider that I have created using resistors, and it will drop the voltage down to 3.3 volt. Okay, so here I have inputting the 5 volt, and using the resistor divider you can see the output amplitude right now is close to 3.3 volt. Okay, so this is the conversion that we are doing using the resistors. You can also input analog signals over here. So here is 2 kilohertz sine wave being inputted into the transmitter, and you need to flip the switch to analog signal, then only it will transmit analog values. And right now in the oscilloscope you will see it is outputting these weird square waves, because on the receiver side as well you have digital output and analog output. So the digital output is this square patch one is digital, and this round one is analog. So as soon as I connect the oscilloscope port probe into the analog output, you can see we are receiving the sine wave. Okay, so this is the sine wave. It is going through the resistor divider again. So here on the board itself you have this gain control. So as I move this potentiometer, you can see the gain is being changed, and the amplitude increases and decreases based on what the whatever I am moving the potentiometer to. And over here You can send this analog signal as well. That is what I wanted to show you. Okay, so this is how a typical UART communication protocol looks like. So the default of the transmission line is basically high. Okay, the transmitting side keeps the line high when it is not sending the data. So on the receiving side, if you see the data is basically pulled high, it basically means that there is no data being sent on the UART line. Data starts to be sent from this. This is the start condition. Okay, so whenever the line is pulled low to 0, the receiver knows that some sort of data has started coming. Okay, so the transmitter pulls the line low and this is the starting period, and following the start bit 8 data bits are sent. Okay, so one by one all the 8 data bits are sent. So here if you see, the first bit is 1, second bit is 1, then we have 0, 1, 1, 1, 0 and 0. This is the 8-bit data that we are sending. Okay, so start bit is basically pulled down 0, basically a 0 bit, and the stop bits need to be 1 bit long again, and this is active high. Okay, this is how the RX knows that we have stopped the communication and data is basically up to here. However, you must have noticed one flaw in this design, that how will the RX know at what intervals to sample, right? What if RX samples all the 8 bits here? It will take all ones, right? So this is the discrepancy. You have to agree upon a rate of data. Okay, so on the TX side and RX side, a rate is agreed upon. Let's say 9600, and at this rate the RX will sample. So that guarantees that RX will sample on the bits and not twice or thrice on the same bit. Okay, yeah, now that I realize, it would be better if I show this on the oscilloscope. So let's put a UART transmitter on an FPGA and let's take a look at the output waveform in an oscilloscope. Alright, so I've hooked up the Nexus 4 DDR board to the analog discovery and I'm transmitting it from PMOD, and I'm picking up the signal through this oscilloscope wires, and here I've opened the scope on my laptop and we are going to capture the signal. So I'll push the button to send these data. Okay, so here you can see the data and I'm going to see the signal over here. So let's capture the signal. Okay, I've stopped it. Yeah, so here you can see this is the UART signal. So by default you can see that the UART line is basically high, and it is high at the VCC, which is 3.3 volts on these Nexus boards. And here you can see this is the start bit, so it pulls the data line down, and this is 0. And as you can see, the data we are sending here is 110011 and 00. These 8 bits we are sending, and here you can see this is the start bit, so this is 11. Okay, so if you look at the width, this is the these are 2 ones over here, so this is 11, 00, 11 and again 00, and this is the stop bit, this high. Okay, and then it stays permanently high over here. So this is how a UART signal looks. Okay, so now that you have seen the UART signals, let me explain this entire setup. Okay, so we have two FPGAs. FPGA first is the transmitter FPGA, and the second one is the receiving FPGA. Okay, so in the day 3 of the 100-day FPGA series, I have explained about the PMOD ports. Okay, so and how you can interface like external hardware with the FPGAs, right? So interfacing and communication between two FPGAs can be done through these PMOD ports itself. Okay, so what's the first step? In that video also I have told you the first step when you are connecting two pieces of hardware is first off you need to short the ground, right? So you need to tie their grounds together so that the reference voltages are the same. And the second wire that we need to connect between these two is the signal wire, right? So this is basically this entire signal will travel through this wire, and this is the reference ground, so that the voltages that is set by the transmitter FPGA is the same when we see it on the receiver FPGA, right? So from the transmitter FPGA, we need to convert our signal into optical signal, right? So we need to give this signal to the EMONA FOTEX board and in the transmitter side, and this will convert the signal, electrical signal, into optical signal. So whatever comes out here is the light basically, and this travels through the optical fiber cable, and then we again insert into the receiver side, okay? And again after you receive it from the receiver side, you convert it into electricity and you give it to the receiver FPGA. So this is the setup, and of course again here as well, since you are interfacing FPGAs with external hardware, you need to tie up the ground. So here what I will do is basically find a ground on the EMONA FOTEX board, and I will just connect the ground of both the FPGAs to the FOTEX board, and these two grounds are internally connected on the board, so on the EMONA FOTEX board. So again these and all the threes are on the same ground, so the voltages they will see is from the same like reference level, okay? So that is important. So this is how the setup is. So now let's see it on the actual hardware. So here is the entire setup that I have explained to you right now. This is the ground reference connected into the FOTEX board to the FPGA, and this is the signal wire connected to the transmitter LEDs. So this is currently transmitting red over here. So right now it is basically, if you basically through the optical fiber you can see red is being transmitted. I will plug this in back into the receiver, and we will basically take the converted output. So let's just plug it in the receiver first. We will take the converted electrical output through this, and I have not connected the analog discovery here. This is connected directly to the voltage divider right here that we have made. Then from the voltage divider to the FPGA. The analog discovery is disconnected from everything right now. So basically this setup, we are taking the electrical output to that FPGA. Right now if I send the data, let's send 3 from this FPGA to that FPGA. We will push the transmitting button. Currently it is 255, as you can see. We transmit, and here you can see that 3 is being received over here, right? So this is basically getting out from the optical fiber back into the electrical signal, and we are receiving it on the FPGA. Alright, so this is cool and all, but I have something cooler to show you. So I'll change the setup a little bit. So an advantage of using light in the communication is that you have a lots of different colors of light, different wavelengths of light, right? So if I am transmitting something using red light, you can also transmit something on the green light, right? So using this principle, we will basically create a setup in which we are sending the UART signals from 2 different FPGAs, okay? And we will send it through 2 different lights. We will combine them, and we will again transmit the combined light, okay? And then on the combined light, when we receive the combined light, we need to separate it, right? Then only we will be able to decode. So for separation we will use filters, and then we will put it in these receiving sites. So this will convert the light back into electricity, and here we can basically receive it on these 2 FPGAs, right? How is the connection gonna look like? So here from the transmitter side, I need to pass the signal wire to one of these LEDs, and from the second transmitter I need to again hook a wire to one of these transmission terminals, okay? So this FPGA, for this FPGA, the transmitting signal is going to be converted into light using this transmitting terminal, and for this FPGA the transmitting signal is going to be converted into light again using this. Now these 2 lights need to be of different wavelengths, because if they are not, we how will we separate those lights, right? If both of them are red, I cannot on the receiving side, I will not be able to separate them, right? So that is why these two lights need to be like separated in the wavelengths. And again, for transmission, what I'm going to do is basically, first off, I will just couple these two optical fibers. So on the FOTEX board there is a coupler, as I've told you. So this coupler over here can take signals and basically combine them. For combining two lights, we need two sources. So here I'm taking a 10 kHz digital signal and 2 kHz sine wave signal into green and red LEDs. And here you can see on the optical fiber we are getting the two colors light over here, and we need to couple these, right? We need to combine these out. Basically combine these two. So here I have combined these two, and the output over here we can get on D as well as C. So I'll take another optical fiber and I will connect it on this output port, basically this coupler port, and on the output, as you can see, we are getting this whitish kind of light, combined green and red light. Okay. So when I put these two signals over here, it basically gives me the added signal. Now this added signal is going to be the basically the combination of these two lights. Now I cannot feed this into any of these receivers because the light is not separated, right? It is not separated because we have the combined light here. Some information is being transmitted from these two FPGAs, and that will cause the combined light to like basically have a behavior that is the summation of these two. So we need to separate this, right? Basically imagine like this is the transmission line, and you have this transmission line going from a certain place to a very different place. Okay, there you need to separate this again. So how do you separate different lights? You have filters. Okay, so you have filters over here. These are the WDM filters here, as you can see, wave division multiplexing filters. This is the red filter. If I input this white light into the red filter, this combined light into the red filter, and take the output over here on this optical fiber, you can see we are getting the red output. Okay, this is the red output that is being transmitted from the red LED. Again, if we take the combined light and input into the green filter and take an optical fiber and see the output of the filter, you can see we are getting the green output. Okay, so if we can basically have both of these over here, and we are separating red and green channels. First off, just take this light and input into the filter, and the output of the filter will be a single light source. Okay, so if we have a red filter, we put the combined light into the red filter and it will give the red output, and it will block every other light sources. Okay, so here again, if we feed this same thing into the green filter, the output will be the green light and it will block every other light. Okay, so then we can basically put into these receivers RX1, RX2, which will convert the light signal into the electricity, and we can then feed these electrical signals into the receiving FPGAs, right? And this is how wave division multiplexing is done. This is known as wavelength division multiplexing. We have used different wavelengths of light here. Okay, this can also be used for duplexing. Okay, full duplexing. That is, you can send, basically, let's say we are using just 2 FPGAs and not 4. We can send data from here using one light, but this guy also can send data using a different light on the same line, on the same optical fiber, and this will allow these two guys to basically talk. Right now I have defined the roles, like this is transmitter and this is receiver, right? This can also be the transmitter, because let's say this guy needs to talk to here. So in that case also we can use a different light, and basically on the same optical fiber I can basically use a different light and transmit this FPGA's information to this FPGA. Okay, so this will can be done on the same optical fiber, and this will be full duplexed system, because the transmission is on the communication is both ways, right? So this full duplexing can also be done using this wavelength division multiplexing. And let's go and see on the hardware how I have done it. These two are the transmitter FPGAs. This is the transmitting line and this is going to this board here. Okay, so currently these two are transmitters, transmitter red, transmitter green, and this is the input, electrical input, optical output over here, and this is the receiver. So if I grab this and take this out, you can see this is optical red and put in the receiver. This is optical green and green light, and if I push it in, and this is in the receiver. Now from the receiver it's getting converted into electricity back again, and we are using a voltage divider to step down the voltage to FPGA limits 3.3 volts. Here it is outputting 5 volts, and now this goes into here, and these second wires are basically just a ground short, and I'm connecting a multimeter from the ground so we can measure potentials. So this transmitting FPGA transmits to this receiving FPGA, and currently right now it's defaulting to 255 right now. I will send, let's say, any value, let's say 3, and I'll push the transmit button over here, and we can say it is 3, traveling from the optical fiber to this FPGA. And similarly, if we use this FPGA, let's transmit 15. So currently it's displaying that. If I push it, it will display 15. Okay, so this is the setup right now, and as you can see, this to transmit, these are two separate channels. Okay, and this we are directly putting this in these receivers. Now what I will do is wave division multiplexing. I will multiplex these two channels, and how I'm going to do that, let's remove these two, and here you can see both the colors. I will put it in the coupler. Okay, so here is the coupler 1 and here is the coupler 2. Let me push it. Okay, now it is coupled. I will take another optical fiber and take the output. Now this is neither green nor red, this is combined light. Okay, now how do we get the data out? How do we get the red and green lights out again? We will use these filters, wave division multiplexing WDM filters, red and green. Okay, so here if I input this one to the red filter and take the output from the red, I'll use another optical fiber, and after this filter, if we take the output from here, okay, now you can see this is red. So it's going from multiplexed output to this filter, and I'm getting red. Okay, I will put this red in the receiver right here, and I have to adjust the intensity again. So right now let's just transmit and see whether we are able to transmit anything. Okay, it's not taking it because the gains are probably not right. Okay, now so I just flipped this to high sensitivity, and right now if I transmit anything, I'm transmitting 15, and I'll hit, you see here, I'll hit transmit button, and you saw at 15. So the light is combining, and this combined light is again filtered, and I'm taking the red light and receiving it over here. Next we also need to do this for green. So what I'll do is take another optical fiber and I'll connect it here to the output of the combined wave, and again you can see this is neither green nor red, this is combined. And if I put it on the green filter, if I put it in the green filter, and I'll take another optical fiber, and we will see the output from the green filter. This is green light. So combined light goes into the green filter, and green filter basically takes the green out. and if I put it in the receiver, and here also I will hit high, and currently this FPGA is doing the green receiving. So if I transmit let's say 7, wait a second, okay, so that wire got loose. Let me transmit 3 right now, and here currently it is 7. So if I transmit from here, it turns into 3. So this is the optical fiber UART with wave division multiplexing. Okay, so hopefully you liked the video, and if you liked it, you can let me know it in the comments, and you can also hit that like button. And if you are interested in all these things, all the hardware related things and FPGA related things, you can subscribe to this channel. And just thanks for watching this video.